Okay, we've arrived at experiment 8 of the dissertation on distance perception with simulated visual field loss. We're going to just dive straight into it. We're going to do methods, results, context for results. Let's go. So to address our hypotheses, we utilized a within-subject factorial design with simulated vision loss, connecting Q, aka cast shadow really, and target distance as factors. And distance judgments were obtained through an absolute measure of egocentric distance perception called blind walking. So with blind walking, someone views an object in space and they are then blindfolded and they walk without vision to where they think the object was. And on average in the real world, so without an HMD on their face, people are quite accurate at making distance judgments with this measure up to about 20 meters. People have made these distance judgments under 3 visual field loss conditions, which you can see depicted below. The no vision loss, center visual field loss, and peripheral visual field loss. And so to simulate these conditions, we employed the vision simulation described in the earlier chapters of this dissertation. This vision simulation, as a reminder, employed a Gaussian image pyramid. And for this particular study, we used a pyramid with 7 levels. The resulting image pyramid for the HTC Vive Pro Eye, which has a resolution of 1400 by 1600 pixels per eye, was 1400 by 1600 pixels per eye at the bottom or top layer, and a resolution of 22 by 25 pixels at that 7th bottom layer. The area of the field of view that was affected by downsampling was then dictated by a radial gradient area, which is really nice for this study because radial visual field loss allows us to model visual field loss perfectly around eccentricity from the center of one's gaze. And so the radius of this circle was set to match 20 degrees eccentricity from the center of the screen. And once eye tracking was enabled, the center of the circle was aligned with the center gaze position of the user. The target object was a cube. It was presented floating just above the ground and rendered with either a realistic low contrast connecting Q, aka cast shadow, on the ground beneath it, or it was rendered with a stylized high contrast connecting Q, or a non-photorealistic cast shadow. And the target Q was actually also presented at random orientations between 0 and 45 degrees. That's a left-right rotation on the y-axis, to improve the generalizability of our experimental results, which is something we looked at, something being the relationship between object orientation and cast shadow, in study 4 of the dissertation. It's been a while. And targets were presented at 2, 2.5, 3, and 3.5 meters, and each unique combination of these experimental factors, distance included, was presented twice to the participant. You may have noticed that the distances we use in the study are a bit closer than what we evaluated in our prior experiments, in which distance judgments were with verbal report were measured at a range of 3 to 6 meters. One of the reasons for this is that we really wanted to use blind walking for this assessment. As a measure of distance perception, it's much less variable than verbal report. And we anticipated the possibility that the impact of visual field loss in the study might be subtle, given that we deliberately do not completely occlude visual information through our simulated vision loss, which means that participants retain some light sensitivity and some very coarse spatial information where vision loss is incurred. However, because we're using blind walking and tethered displays, we need to account for the length of the cord. So we reined in our distances a bit to ensure that participants could not use the cord tension as feedback during blind walking judgments. The experiment was blocked by visual field loss condition, and the order in which visual field loss conditions were experienced was counterbalanced across participants. All other experimental factors were pseudo-randomized within each block so that participants viewed each unique combination of stimuli once before experiencing that same stimuli combination again. Overall, we collected data from 24 participants, 14 of which were female, 10 male, and age between 20 and 38. And each participant completed a total of 48 trials during the experiment. So with 24 participants, this gives us a total of 846 trials collected overall. A couple of notes on the experimental procedure before we dive into our analyses. Before every block of experimental trials, participants were acclimated to their assigned vision loss condition. So center vision loss is going to play here. So during this acclimation phase, the participant was required to explore a separate virtual environment and walk around that environment for a minimum of 2 minutes. This acclimation phase served an important purpose. It allowed participants to familiarize themselves with their altered sensory input associated with the vision loss conditions. So now here we see the peripheral vision loss playing. No, the participant could not see the mouse. That's a screen grab artifact because I forgot to move it. But yeah, so in this way, participants were allowed to develop strategies to compensate for the simulated impairment. And without acclimation, distance judgment performance could underestimate participants' true abilities or overestimate the impact of the vision simulation impairment conditions. So on the left, you can see a static image of the acclimation virtual environment, and on the right, you can see a static image of the experiment virtual environment. Both scenes were intentionally rendered with detailed textures and objects because we wanted the environment itself to be representative of the rich visual information someone might encounter in reality or in a real application. To answer our research questions on how depth perception judgments vary with simulated vision field loss and visibility of connecting cues, we used a linear mixed effects model, the formula for which you can see below here. We actually use the same formula for both analyses, so keep that in mind. But to support our primary measure of interest, we also analyzed participant response times for each trial, where response times corresponded to the interval of time between when the target was presented to the user and when the user verbally indicated that they were ready to make a distance judgment through blind walking. Response times can be really informative for this kind of evaluation, and we can think about this through the lens of experiments on task performance with real patients with severe vision loss. Often these individuals are able to achieve similar performance to individuals without vision loss because people are smart and they're adaptive. They develop strategies over time to compensate for their vision loss. However, even when performance is similar, people with severe vision loss often have slower response times, which is due in part to these compensation strategies. So for this analysis of response time data, we used a generalized mixed model with a gamma distribution, which is one of the common distributions used to model response time data. Overall, participants underestimated distances by 14.9% in this experiment. This amount of underestimation is in line with prior distance estimation studies in VR. But what was the effect of visual field loss? Disclaimer, my hypothesis was that central vision loss was going to result in significantly different responses from people for reasons we'll discuss on the next slide. But what actually happened was people underestimated distances even more in the peripheral vision loss condition. Was this surprising? Was it expected? In my opinion, it's a little bit of both. If we just look at this from VR research display perspective, several experiments have already shown that when you restrict field of view, people's sense of space becomes more compressed, hence, distance compression as well. But these experiments have evaluated mostly complete peripheral vision loss because they're modeling their experiments based on the properties of these head-mounted displays, which complete occlude. However, there's a series of studies from Adam Jones initially and then later Scott Cull's group that can provide us some context. So this prior work found that something as simple as just adding light to the periphery can help enhance, mitigate some of that distance compression that we find in VR displays. What's particularly interesting for us is moving forward into 2018, Lee et al. Down there is they looked at this peripheral just pixelation field. They just downsampled. And they described the results of this work in the context of their prior evaluations, and they discussed that the results from that study were actually quite similar to the unaltered display. Which brings to the question, why do we then find distance compression in this work? There's a few possible explanations. One, it might have to do with your peripheral vision is really sensitive to edge detection and motion. So perhaps because we use this smooth blur, people didn't feel compelled to visually scan their environment to gather information that they needed, the spatial information that they needed to make more accurate distance judgments. Another possibility is to do with the experimental protocol itself, where egocentric distance estimates to targets that are in front of you. You don't have to visually scan necessarily. That I have put less stock in because these prior studies have used the same protocol. However, it does feed into that potentially stimulating the peripheral field of view to encourage people to look around idea a bit. It's definitely an interesting area for future work. Meanwhile, I had predicted that there was going to be a main effect of central vision loss, and specifically I expected that people would overestimate with central vision loss compared to the no vision loss condition for reasons that we're going to talk about now, because it's relevant for our vision shadow interaction. Because we designed this high contrast surface contact cue with the central vision loss folks in mind, because I know it's like beating a dead horse. You've heard a lot about surface contact from me at this point. When visual information is unclear and surface contact cues are missing, like for example, you can't see them because you have a blur in your center vision, people rely on optical contact. So objects, when you rely on that method, appear farther away. So in the absence of surface contact cues, you feel them farther away. We did find that here, where people overestimated the low contrast shadow condition relative to the high contrast shadow condition. So that hypothesis tracks. Although the effect was smaller than one might expect, it's only that beta value is a 0.05, which is 5 centimeters. And it's likely to do with the experimental stimuli and the distances we used. The cube was not offset that high off the ground. I suspect you might find more dramatic effects of visual aids at closer distances and with methods that involve more fine motor control. Another thing that we looked at that we want to talk about today was effects of order. So I actually used Bonferroni correction on all comparisons with more than 2 levels of factor, and so this ended up not being statistically significant. But it's something to keep in mind. There was a trend in sense that the first block, there was a little more distance underestimation, which makes sense because it's the first block of trials and people are adapting to the paradigm. We did allow for a little blind walking training in the sense that people were able to walk around with their eyes closed. However, we didn't have them do like a formal blind walking protocol training assessment. And there were also no interaction effects. So fortunately, this shouldn't have had a major impact on our experimental results beyond adding perhaps like a little bit of additional underestimation overall. So one of our explanatory measures that we looked at was response time. And so for this, we found that central vision loss people had longer response times when viewing targets. And this makes sense because participants couldn't actually view the targets with the 20 degrees scotoma at the center. So they had to develop compensation strategies to view the target and perceive where it was in space, which causes time. So for response times, we did find a significant main effect of order. We didn't find any interactions whatsoever. So in the first block, people had longer response times, which makes sense because people, even with debriefing, as they familiarize with an experiment, they tend to perform faster. So we know that peripheral vision is really important for spatial perception. Beyond the things we mentioned earlier, even peripheral vision is essential for understanding things like spatial layout and one's orientation in space. There are certainly conditions in which field of view restrictions impair depth perception judgments, but this isn't always the case, as we saw earlier. And if we look at the context of real low vision patients, depth perception studies with these populations are often somewhat equivocal. So there's definitely still much more room for improving our understanding of how peripheral vision and its absence or degradation in the case of these 2 studies impacts people's depth perception. From an accessibility perspective, this initial study in which stylized graphics were shown to have a modest but significant effect and a positive impact on depth perception for people with simulated central vision loss is really, it's an encouraging initial study. Better yet, we have this platform that we can now use to control visual field, the extent of visual field loss. Like in this study, it's really limited, right? It's this one size scotoma, eccentricity for peripheral and for central vision loss. And then we're looking at this target. It's very specific tasks. Our target is presented at kind of narrow range of distances, which is less important for distance perception, but it is important for the size of the visual image on the retina, which for central vision loss. But this is great because a nice start because the simulation can be used to further our understanding of human perception and behavior. For example, the role of peripheral vision loss. It can also be used in a more applied way to help developers and designers to more rapidly assess accessibility solutions. With the caveat that this is by no means, this is really like a crude approximation of a real low vision patient, and you should always consult real patients before designing something for them. But at the least it can facilitate development. Yeah, for this study as well as for the rest of the dissertation, they've laid the groundwork for a lot of really interesting potential future directions, whether that's in the realm of computer graphics and, say, augmented reality displays and pushing the limits of what those systems are capable of to benefit visual perception, from accessibility, from an applied perspective in designing better applications, or from a research perspective of understanding the user base more through simulating one aspect of their vision impairment through just better understanding human behavior in general. And I'm out of time, so that is all for now. Thank you for listening.